The sun sinks below the horizon. The serenity of night draws near. Soon the Earth will turn in harmony with the cosmos. But not necessarily in harmony with our star. The sun is sending us ominous warnings that we ignore at our peril. A roiling deep within. Energy building in its outer zones. An eruption gathering force. We are getting better and better at reading the flare-ups, the waves, and the spots that emerge on the solar surface. But our increasingly technological society has exposed us as never before to the sun's angry moods. The wake-up call arrived in the year 2003, with Halloween approaching. A truly scary chain of events overtook our solar system. "93 million miles away, the sun began to vent its rage. On its surface, dark regions called sunspots appeared unexpectedly, a sign of rising tension within. It had been 3.5 years since the sun last erupted in fury, at the peak of an 11-year cycle of solar flare-ups. Back then we got ready for it by shutting down satellites that were vulnerable to high levels of radiation. No one expected this. The sun erupted in a series of massive explosions called coronal mass ejections, or CMEs. Vast electrified gas clouds raced outward. Solar telescopes recorded the action. The largest emission of solar X-rays ever seen. Flares reaching tens of thousands of miles into space. And a wave of charged particles traveling at 8 million kilometers per hour. The sun became a giant plasma weapon, more potent than any in science fiction, and pointed right at our home planet. On Earth, the Halloween storms produced some of the most spectacular auroras ever seen at the North and South Poles. They occur when a wave of charged particles from the sun interacts with Earth's magnetic field in the outer regions of the atmosphere. Beautiful and awe-inspiring, they were once identified as the dancing of spirits, or as signs from God. But as lovely a light show as this is, it means there are kilovolts of electricity in the air, looking for places to get down to the Earth. The Halloween solar storms brought jolts of electricity that impacted power grids around the world. In space, they damaged 28 communication satellites and destroyed 2. A newly installed GPS-based air navigation system went down for 30 hours. This energetic surge did not stop there. Sweeping past Mars, it was so strong that it burned out the radiation monitor aboard the spacecraft Mars Global Surveyor. Ironically, this instrument was designed to study radiation that human explorers might encounter on future missions beyond Earth. Months later, the same rush of solar energy washed over the two Voyager spacecraft on their way to the far reaches of the solar system. Coronal mass ejections like this have been known to blast their way out to where the solar wind meets the flow of particles around the galaxy itself. The Halloween solar storm of 2003 was by no means the worst. The standard was set in the year 1859. Just after midnight on September 2nd, some campers in the Rocky Mountains were awakened, they said, by an auroral light so bright that one could easily read common print. In New York City, thousands gathered on sidewalks and rooftops to watch the light show. An observer in Havana, Cuba, reported that the sky appeared stained with blood and in a state of general conflagration. The day before, a British amateur astronomer named Richard Carrington had seen signs of what was to come. He observed an outburst of intensely bright and white light from a large group of sunspots. The eruption took aim at the Victorian version of the Internet, causing major disruptions to telegraph networks. It was a preview of the risks to our modern technological society. Like a major hurricane or an earthquake, a solar storm like the one in 1859 is a rare event with potentially significant consequences. The risks today were in stark evidence in March 1989, when a solar outburst took down Canada's Hydro-Quebec power grid, leaving 6 million people without power for up to 9 hours. Not long after, we launched the first generation of satellites designed to provide real-time data on the Sun, including the ACE and SOHO missions. Meanwhile, the threat keeps getting worse because solar events can strike at the technological networks that increasingly define modern life. Among the most vulnerable are those that rely on GPS coordinates. Then there's spacecraft, jammed with sensitive electronics, as well as astronauts. Aircraft, especially those traveling over the poles. And energy systems. To the electric power grids that bind civilization together, we are adding an array of renewable sources, including wind farms, solar arrays, and nuclear plants. This grid is getting larger, more varied and smarter. There is a microprocessor in almost every device, communicating and negotiating with one another, running everything from air conditioners to power plants. Add to that hundreds of miles of new broadband internet lines into our houses, and all those expensive smartphones tucked into our pockets. The more integrated our technological infrastructure becomes, the more vulnerable it is. A recent estimate published by the National Academy of Sciences says that an outburst like the one in 1859 could cause damages of $1 to $2 trillion in the first year alone. It's not only the cost of repairing and replacing damaged components, but also the lost business and government services extending over the years it takes to recover. To understand what a powerful force the Sun can be, take a look at Venus. At almost exactly the same size and mass as Earth, it's truly our sister planet. Scientists have found that solar winds are steadily stripping off lighter water molecules in its upper atmosphere. What's left is a witch's brew of acetic gases and carbon dioxide that have thickened at lower altitudes, rising to some 90 times the density of Earth's atmosphere. At a concentration of 95% in Venus's atmosphere, CO2 gas trapped increasing amounts of sunlight and helped drive surface temperatures up to 464 degrees Celsius, hot enough to melt lead. How did Earth avoid such a harsh fate? For one thing, our planet has a natural defense system that Venus lacks. Earth spins around on its axis once every 24 hours or so. This has an effect on molten iron welling up from deep in its core. Like an electric dynamo, these plumes of hot metal generate magnetic fields that extend beyond our atmosphere, enveloping the Earth in a protective shield called the magnetosphere. Watch what happened after this solar eruption, recorded by satellites on December 13, 2006. A simulation of the blast wave shows its truly immense reach, well above and below the orbits of the planets. Sweeping by Venus, it takes aim at our planet. The wave slams into and depletes the outer surface of Earth's magnetosphere. Plasma carried by the blast now flows by Earth. The magnetosphere responds by stretching out into a long, thin structure. While Earth's magnetic field may be strong, it's not impenetrable. When energy from the Sun builds to a critical threshold, hordes of charged particles move out along field lines, wrapping around the Earth, and finally flowing in. Now channeled and concentrated around Earth's poles, these particles suddenly snap, inducing huge jolts of current, strong enough to wreck spacecraft and blow out power transformers on the ground. According to recent satellite findings, the danger is enhanced when the magnetic fields of Earth and the Sun are oriented in the same direction. With our vulnerability to these cosmic power surges growing, we have launched a whole new generation of spacecraft to monitor the Sun. They've taken up positions in low Earth orbit. They are out plying the margins of the magnetosphere. And they're circling far out in interplanetary space to get a good clear look at changes on the solar surface. With data flowing in, scientists are drawing an